Today I'm going to discuss about this talk, deep learning algorithms and its application. So in this talk, I will start with the introduction of like deep learning. And before deep learning, as we will work on image data set. So little bit introduction of image data set, then deep learning, then what is the difference between machine learning and deep learning. Then we will discuss different applications of this deep learning in different environment, specifically in medical imaging domain, medical image domain. So I hope in this 90 minutes, you can find something useful. And in between, if you have any question, please feel free to interrupt me, stop me. Or if you are not comfortable in asking a question in between, then feel free to ask at the end of talk, right? So let's start my talk. So let's start a talk with one of the very beautiful picture because we are talking for deep learning, and one of the application of deep learning is in a computer vision. So here let's start just kinds of case study related to computer vision, so you can understand about this computer vision in a better way. I hope like many of you are aware about computer vision, basic computer vision definition, but if few of you are not aware, then you will understand with the help of this case study. So in front of you, there is one beautiful picture and with one famous quote. And the quote is one picture is worth more than 1,000 words. So everyone is aware about this quote. So that means if we are keeping one picture and we are writing 500 or thousands of words, then people will prefer to give answer by picture, right? Because people like visualization, like like to see the things in comparison to reading the things and doing the hard work. They want some like smart work or easy work like that. Okay, so there is a picture in front of you, and in this picture you can see many things there are two tractors, road is there, hill area is there, greenery area is there, right? Beautiful colors of skies, right? And a small village is there, right? So many things you can see, right? And grass and so many things you can see. So we are looking all these things. Who we are human being, means we are a human being are looking these images or like this particular image, and from this image we are interpreting the information. Interpreting the information means we are like finding their tractors, their small village, hill area, like that. Okay, so many things we are going to find from this image when we are human being. So this is called human vision, right? Human vision. Now, if same task is done by computer, then it's called computer vision. That means computer is going to identify there are tractors, there is a village, there is a hill area, like beautiful colors of skies. If like computer is going to identify all these things, then it's called computer vision. So the definition of computer vision will be interpreting the contents from image and video data set. Is called computer vision. Means computer is going to be interpret the contents from image and video data set. That's called computer vision. So here, this is the basic introduction of computer vision. Little bit, if you go little bit more towards this computer vision side, and we use deep learning techniques for computer vision, right? So we will come back to that point also. So object detection is one of the object detection is one of the type of computer vision techniques. And here object detection means we are detecting the object, means if you're talking for a video data set, then we are detecting moving object from the video data set. So there is a basic concept of object detection is like there is an intensity changes between successive video frames. Like for example, there is a one video frame. Video frame means let me explore with little bit more basic. Uh, there is an image and there is a video. So video is a collection of frames. I think you know, right? Video is a temporal sequences of frames. Means so many video frames we are putting all together, and that will be formed as a video, For example, it depends on the like video quality standard. So there might be a 20 frames per second, there might be 25, there might be 30 frames per second. So like for example, we are talking about 25 frames per second is standard video. Then that means there are 25 frames in a second, right? And these frames move so uh, like so fast, like our eyes can't visualize like these are the separate images. We think like this is a complete flow, right? This is a flow of the video. So if you're talking for video, then in a video there are frames, one frame, next frame, like that. Okay, so if like video is playing, and then in this video, the human being will move from one place to another place. So how will you identify the human beings are moving? Because if you're talking for frames, in a frames, in a particular frame, like there are intensity, right? Whatever color we are going to look in the video frame, that color is represented by intensity value, right? So if we are going from one frame to another frame, let's say, let me explain one example. If you're going from one frame to another frame, like this is a one frame, and this is a next frame, like this is a tth frame, right? And this is t plus 1th frame. This is ts plus 1th frame. So here, for example, there's a moving object. One person is there, right? One person is there. Now, and let's say there is a hand of this person at this particular position. Now we are taking another frame, right? So in another frame, the same person, right? Same person like this, okay? But the hand is on a different direction like this, okay? So here easily we can find this the difference between one frame to another frame. Obviously, in real life, that much not like that much difference will not be there from one frame to another frame, but there will be a difference. So here, like for this particular location, there will be different intensity value. For other particular location, there will be different intensity value. So if we can find the difference between this tth frame and t plus 1th frame, then we can say like there will be a moving object. Why? Because if there's a background means zero. Background means this white background is there, right? 255 value. And if you are using foreground will have some other value, right? So if you subtract background to background, there will not be any change. Means 225, 255 minus 255, zero, right? So everywhere there will be zero except that particular location, So in this different, like whatever, like whatever frame we are getting, right? After subtracting from one frame to another frame, whatever frame we are getting, in that we will find something different, right? Some difference point we will find. So according to the difference points, we can say these are the moving object part, right? Moving object part. So this is the core idea behind this moving object detection. Whatever algorithm you are using for moving object detection, they use this idea. So what is the idea? Underlying assumption is that moving object generally entail intensity changes between consecutive frames. If we are going from one frame to another frame, then there is change in the intensity. If we can find that particular change, then we can find the moving object. So let's see this example. Here we have like a particular frame from like let's say supermarket data set where people are moving from one place to another place. So like one person, second, third, fourth, like person and other persons are there, right? They're moving from one place to another place. What we'll do, we will subtract like this frame to the next frame. Like we'll take one more frame like this. Let's say this is a tth frame, and we'll take one more t plus 1th frame. We'll subtract from t plus 1 to tth frame. If we'll subtract, then we'll get something like this mask, right? And we'll get this mask, and in this mask, what will be available? Moving object part will be available. Like moving object parts will be available. Moving object parts will be available, right? Like this. But along with this moving object parts, we'll get some noisy part, right? Noisy part. This noise might come due to illumination variation, due to different lighting effect, due to camera shaking. So many reasons are there, right? So due to that, like we are getting this mask, this noise, because This noise we are getting because this background, for example, here the light is illuminating, right? So here like this background will become a foreground because in next frame this light might change, right? So this background will become foreground and it will come here, right? So for that purpose, like, but we are interested only in moving object part. So what we are doing, we are going to apply some post processing on this moving object detection. Some post processing techniques like morphological operation or some other like different types of mathematical operation we apply to reduce that noise. So we are going to apply some morphological operation, right? Then we'll get this clear part, right? After post processing, we'll get the clear part. Now, what we will do in this clear part, we will take this location, right? We'll find the coordinate points of this person. Similarly, we'll find the coordinate points of this person like that. We'll find the coordinate of this person like that. Okay, so we'll find different coordinates and we will overlap these bounding boxes on the original video frame, right? On the original video frame. Once we'll overlap, we'll get these bounding boxes here, right? So this is a way by which we can detect the moving object, and this is the concept, core concept behind this moving object detection algorithm. There are so many approaches are there for moving object detection, like or if you're talking for traditional approaches, then frame differencing, background subtraction, optical flow-based approaches. If you're talking for newer approaches, then new like people are using RCNN, right? Fast RCNN, faster RCNN, YOLO, different version of YOLOs are there. So these all algorithms are used for moving object detection, and all the algorithms are based on this similar concept, right? I hope it is clear to everyone. Now, next part of computer vision is object tracking. Here, what we are doing, we are going to do, we are tracking the particular object, moving object in successive video frames corresponding to initial video frame. Similar to object detection, here for example, in the first video frame, we are defining the object like we need to track this particular person. Now in successive video frame, we need to track that particular object, right? So the object tracking means finding the position and size of a object in successive video frame corresponding to initial video frames, right? So this is the way we do object tracking, and it's very like simple and similar to this moving object detection. Next is object recognition. So object recognition means identifying the particular object name, right? So for example, we are talking about a smart home concept. So in a smart home, just like our software can identify whether it's a TV monitor, the sofa, pillow, stove, right? A bookshelf, desk. So like so many things we can identify with the help of object recognition techniques. So here also like we can use different deep learning algorithms, right? Yeah, like YOLO and other algorithms we can use for that purpose. CNN we can use for that purpose, right? Now for solving all these problems, like whatever problems, like few problems we discussed over object detection, object tracking, object recognition, for solving all these problems, we are using deep learning algorithm, right? We are using deep learning algorithms. So let's start with the basic of deep learning. What is deep learning, and how like this deep learning came, what inspired these deep learning algorithms and all those things. So before going to the definition of deep learning, let's discuss this one of the famous diagram. Almost all person might have seen this diagram earlier. So on the top of this diagram, there's artificial intelligence. Artificial intelligence means machine mimic the behavior of a human being. Means machine work like a human being, right? So there might be some famous example of artificial intelligence like autonomous car, right? Robot, there where machine work like a human being. Then the sub part of artificial intelligence is machine learning. Machine learning means learning from experience, learning from data set. Based on the experience, based on the data set, machine explore the things, right? And explore the things, and they can predict the output for unknown input also with the help of this machine learning algorithm, right? So like so many examples are there for machine learning algorithms like supervised and supervised learning algorithm. If you are talking about supervised, then like k nearest neighbor algorithm, support vector machine, like artificial neural network and so many others algorithm, right? So in this way, we can define this machine learning. Next subpart of machine learning is deep learning algorithm. So here, deep learning is the subpart or subset of machine learning, means and it is inspired from human and deep learning, we can say like it is an advanced version of artificial neural network, and artificial neural network was inspired from human brain neurons, right? Like for example, in our brain there are millions of neurons, right? And these neurons are connected with each other, and due to that connection we take decision, right? We do work like that. In the same way, in artificial neural network there are layers. In layers there are neurons. These neurons are connected to each other, and using that connection, like we take decision, right? So this is the way like we do apply this deep learning algorithm. Like, and then in artificial neural network we have layers, right? As I told you, input layer, output layer, and hidden layers. But in ANN, we cannot take so many layers, right? We cannot take like, for example, 20 layers, 30 layers like that. We can't take. If we'll take 20, 30 layers in ANN, then our model will overfit, right? It will not give very good accuracy in test case. So for that purpose, deep learning concept came into the picture. In deep learning, we can have higher number of layers without involving, without incorporating the problem of overfitting, right? So that's why this deep learning came into the picture, and specifically we use this deep learning for large data set. If we have a large data set, then in most of the cases, the machine learning algorithm and this artificial neural network will not work effectively. Then we need to go for this deep learning one, right? So if you have a large data set, then it will give you good performance, deep learning algorithm, right? And the target of both deep learning and machine learning algorithm is to find the model. Model means to find a model, and that model can predict the output for unknown input, right? We need to find the model, and that model can predict the output for unknown input. Model means intelligent, you can say intelligent device, or you can say intelligent actor, right? So that can predict the output for unknown input. So that model we need to identify. So we'll learn all these things in upcoming slides, how we can do that, how we can train the model and the things, right? So let's see one more basic difference between machine learning and deep learning. Although deep learning is a part of machine learning, but if we talk about, specifically we are talking for machine learning algorithm, then here in machine learning, like what we have input. From input, we extract the feature. We extract the features, meaning human being extract the features like manually, like that maybe data scientist or some other clinician or some other person, if you're talking medical domain, then they extract the features. And these extracted features are going to be input, going to be as an input in a classification part, right? We are giving these extracted features as an input to the classification part. Classification part means it can be any of the machine learning algorithm. Here, the structure of ANN is shown, but like we can use ANN or other different other machine learning algorithm for classification. Then this classification network or algorithm will give you output whether it's a car or not car. So this is the part of machine learning. If you're talking about deep learning one, deep learning means like we are taking input, no need to extract the features manually, and just give raw input into the network, right? And then our deep learning model means deep learning model will take care of everything like feature extraction as well as classification, right? And it will generate the output. So that's why deep learning model is called end-to-end approach. Deep learning approach is called end-to-end approach because it takes care of feature extraction as well as classification. So this is the basic difference between machine learning and deep learning approach. So if we are talking, we are going in a little bit more deeper side of deep learning, then there are different types of architectures available for deep learning, right? So these architectures are like CNN, convolution neural network. So which one of the very famous architecture for image and video data set, right? So if you're talking for application of CNN, then it's image recognition, video analysis, natural language processing like that. Then we have RNN, recurrent neural network, mostly used for speech recognition, handwriting recognition, machine translation, and towards the NLP side, right? Natural language processing side. Then we have LSTM and gated recurrent unit network, similar to RNN, little bit advanced version of RNN. Here we work on natural language text compression, handwriting recognition, each speech recognition, gesture recognition, image captioning like that. Then we have a deep belief network. So in deep belief network, we have image recognition, information retrieval, and other things, failure prediction like that. Then we have a deep stacking network, like again, same information retrieval, continuous speech recognition. Right. So these are the different variants, different architectures of deep learning algorithm. And we are not going to cover all these architecture in this talk. We can't cover because like we need time. So we will cover a CNN in this architecture, right? We'll go for the convolutional neural network, and we will try to solve the problem or problem of image and video domain. Like we will try to solve the problem using CNN for the image and video domain. So H, we are going to discuss about CNN. Then you should know about the image also, right? So let's have a brief introduction of image data set. Although I understand you might be aware about image data set, but a few of you might not be aware about the basic mechanism of image data set. So if you're talking for image, then image we call that as a two-dimensional intensity function. Two-dimensional intensity function means fx comma y. Two-dimensional intensity function fx comma y. So if you're talking for fx comma y means intensity function, then we call this as a f. This function is f, right? This is f. This function is called, and matrix is called f. What is x comma y? X comma y is the coordinates. Like if you're talking about row 0, 1, 2, like that, 3, like that, okay? And like the 0, 1, 2, like that, right? 3, 4, 5, like that. Okay. So here, if you're talking for x comma y, then the coordinate is 0, 0, 0, 1, 0, 2, 0, 3, like that. Okay, so all coordinates are represented. And at each coordinate location, we have some value. That value is called pixel. That position is called pixel, and the value is called intensity, right? So we have intensity 128, 127, 1. So here, if value is 0 or near to 0, then that will be black. If value is 255, right? Maximum value is 255, intensity value 255 or near to 255, then it will be white, right? So here the value is 128. That means just in the middle of 0 and 255. So it is a gray, right? This is a 255. That's why it's a white color. This is a 120. There's a little bit gray side. Like that, we can represent the complete image, right? So here we are talking for grayscale image. Grayscale image means like we have only one channel. Here we have only one channel. That's called grayscale image. If you're talking for color image, then we might have, depends on the standard of image. We might have three channels. We might have four channels. Let's say we are talking for RGB image, red, green, blue image. In red, green, blue image, we have only three channels, red channel, blue channel, green channel. And this, like, each channel will represent a particular each channel will represent a particular different kinds of color. Okay, so if you're talking about grayscale image, then only one channel. If you're talking about color image, then there will be three channels, right? So this is the way like we can represent this digital image, and we can find the answer. We can go for this. Now after image, there is a next part is image process, pre-processing or image processing. So processing of image means like we are applying some function, applying some transformation on a particular image. For example, we have fx comma y, the particular image. On this image, we are applying some transformation, right? We are applying some transformation. Let's say, just discuss in terms of example. Let's say our image, in an image there is a problem, like there's a noise in the image, right? Then if you want to reduce that particular noise, then we need to apply transformer. This transformer T we need to apply, right? So once we'll apply transformer, we'll get another image gx comma y, and this x comma y will be same. Means size of image will be same in most of the cases, and that image will be g. Maybe because we are talking, we are calling this as a g because it's a different image. Means this is a, like for example, this is a noisy image, then this is a denoised image, like that. Okay. So image pre-processing means we are going to reduce the noise, we are going to smooth or like reconstruct the image, and so many different types of operations we can apply. So all these operations we represented here with the help of T-able transformer, just general term. Okay, so this is the image processing. And why we need image processing? To improve pictorial information for human interpretation. Means we are going to improve the picture for human interpretation so human can understand it clearly. For processing the data for storage and efficient transformation, like for example, image compression, video compression. Right? So for example, you are in your mobile phone takes image and each image size is 1 MB and you have 1000 such images, right? Then 1000 multiply 1 MB. So 1000 MB like of your external storage is going to be like consumed by those images. So what is the efficient way? You can compress those images. So many other images can also be stored. So for that purpose, we use image processing, right? So now here, this image processing has three different parts like low level process, middle level process, and high level process. If you're talking for low level process, then we have input as an image and output as image. So here, like example of like noise removal and image sharpening, means some noisy image there as an input, and we are in output we are getting clear version of image. Now this image we can give as input to this middle level process, and we can generate attribute like for example object recognition segment. Now you know object recognition, right? So we need to recognize the object. We are segmenting the object into different part, right, based on this attribute. And high level processing means we are giving it an attribute and we are generating understanding, means scene understanding, autonomous navigation, autonomous car. So three level of processes are there: low level process, middle level process, and high level process. And these are the things. And here there are different definition in different books, but in most of the cases people consider this middle level process and high level process as the computer vision, right? These are the computer vision part. And few people believe there's only high level process is the part of computer vision, right? So but in most of the cases these two steps are the part of computer vision, right? And this is the simple basic image processing technique that can be solved with the help of filters, right? So let's little bit explore more about the filter, right? And we will relate this filtering things with our CNN model, right? That's why I'm teaching a filter here. Now we understood about image, we understood about a pixel, right? We understood about the image location x comma y. So for example, there's an image in front of you, image fx comma y. Now in this image, there's a pixel location e. There's a particular pixel, and the value of that pixel intensity is e, right? So now what you need to do, you need to like you need to apply filter on this particular image, right? That can be any filter, right? So we are going to apply one of the spatial filter, right? So spatial filter, if you want to apply spatial filter, spatial means we need to work with neighbors, right? We need to work with the help of neighbors. So let's say we are taking filter size 3 cross 3. So if you're taking filter size 3 cross 3, right? So that pixel will come in center and it will be surrounded by their 3 cross 3 neighbors like this. Now what we need to do, we need to take out the intensity value of all these pixels, right? Center pixel along with all neighbors. So for example, intensity values are like A, B, C, D, E, F, G, H, I. Now what we need to do next, we need to apply 3 cross 3 filter, right? As we have taken 3 cross 3 window earlier, right here, then we can apply only 3 cross 3 filter. So we need to apply 3 cross 3 filter. What we'll do, we'll take this filter value. Let's say for example, filter value is filter values are like JKL, MNO, PQR. Then we need to apply this filtering, means convolution operation we need to apply. So for that purpose, what we'll do, we'll multiply element by element. So for example, A multiply by J, right? B multiply by K, C multiply by L, like that. And we will find the summation of every like multiplication like this. So n multiply by e, j multiply by a, k multiply by like that. We will multiply each of the term, and that will be e processed. So this e will be replaced by this e processed value. So this is the filtering process, right? This is called filtering process. Now this is the step, like whatever, this is a single step for a particular pixel value, right? For a single pixel value. Now the similar kinds of step we can apply for this one, this one, this one, this one, like that. For all values we can apply similar kinds of step, right? Just drag this window, like drag here, right? We can apply for this one, then drag here, we can apply for this one, like that. So for complete image, we can process this one, right? So the same thing I wrote here. The above is repeated for every pixel in the original image to generate the filtered image. Now, whatever we understood is spatial filtering mechanism. Let's explore this mechanism for convolution neural network part, right? For CNN part. So convolution neural network is a deep learning algorithm which can take an input image, assign importance, means weight and bias to various aspect object in the image to able to differentiate one from the another. The pre-processing required in CNN is much lower as compared to other algorithm. So in CNN, pre-processing required is lower than the other algorithm. So we will explore the CNN now. And let's understand the CNN algorithm with one of the very famous architecture, famous and old architecture, LeNet model. Right. In this LeNet model, there are just only 5 different types of layer, 5 types of layers. Right, 5 layers are there. If you're talking for CNN, convolution neural network, which is a kind of deep learning architecture, in CNN, there are 3 main different types of layer. Right? 3 main different types of layers. First one is convolution, next is pooling, and third one is fully connected layer. Let's start with the convolution layer. So here the task of convolution layer is to find the features, right? To identify the features. As we learned earlier, as I showed you here, right? Here, if you apply deep learning algorithm, then deep learning algorithm can extract the features as well as do the classification. So here, if you see, if you're talking for convolution layer, then convolution layer is used to extract the features, right? Next layer is pooling. So that can be max pooling, mean pooling, average pooling, median pooling, and like that. So pooling is used to reduce the complexity for downsampling purpose. And then next is the fully connected layer, in which like fully connected layer is used for classification purpose. Right, so we use softmax sigmoid activation function. I will explain this thing, right? In what case, like we need to use softmax, and in what case we need to use sigmoid activation function. So here there's a one famous architecture LeNet model in which like we are going to give input as a 32 cross 32 image, and we are going to find we are going to apply CNN convolution layer, not CNN, it's convolution layer, right? So here we are going to apply convolution layer with 6 filters, 1, 2, 3, 4, 5, 6, like that. And we are getting this output. At this moment, just you can understand this is the input, this is the output, this is the input, this is the output for all these things, right? And this is a convolution layer, this is a pooling, convolution layer again, pooling layer, fully connected layers. I will explain each of this point in a very detail, right? So don't worry about this thing if you're not understanding at this moment. I will come back to this slide, right? So what I'm going to do, one by one, I will explain all these layers. Like first, I'm going to explain convolution layer. Then I will come back to this figure. Then I will explain pooling layer. Again, I will come back. Then fully connected layer will come back, right? So then you will understand all these things, how these values are coming, okay? So for understanding convolution layer, let's see this architecture in bit more detail. For example, we have an input image, just like an input image, we have a car, and we are doing the task of vehicle classification. There are so many types of vehicles like car, van, truck, bicycle, bike, like that. Okay, so we are classifying these vehicles in different categories, and we have a car, and we are applying these vehicle things on convolution layer, right? Convolution and ReLU, we are going to apply ReLU activation function. Then we are applying pooling, then again convolution, ReLU, and pooling. Right. So this can be many times, right? Convolution, ReLU, convolution, ReLU, and pooling, convolution, ReLU, and pooling. This can be many times. Depends on your data set. Depends on your application, right? How complex your data set is, right? So according to that, we need to select these layers. So this part used for feature extraction or feature learning, right? So convolution layer and pooling layer, convolution and pooling layers are used for feature extraction and feature learning, right? Next, once we have once we extracted the features, and this is the these extracted features are in two-dimensional format, right? Two-dimensional format, 2D format, right? We already know, right? Because two-dimensional image we have given as an input, so this 2D format, two-dimensional format, we are going to generate the image. Now, from that two-dimensional format, 2D image, next part is to apply fully connected layer, right? And if we are talking about fully connected layer, then fully connected layer is one dimension. It want like fully connected layer wants one dimension input, one dimension input, right? So, and this is the two dimension one. So we need to convert this two dimension input to one dimension one. How we'll do that? We can do it easily with the help of flatten operation. But if you want to understand how we are going to do, then let's take one example here. For example, this is an image. In this image, we have values like 1, 2, let's say 4, 5, 6, 9, right? 11, like that. 6 again, right? This is a one dimension one. This is two dimension image. Two-dimensional image feature value. If you want to convert this image to one dimension one, then how we can do that? Just take one dimension vector. Okay. And in this one dimension, we can do like 1, 2, 4, 5, 6, 9, 11, 6. Okay. Like that, we can do this two dimension to one dimension conversion. So this is the way like we can apply all these like two dimension to one dimension conversion, and we can get this operation like we can get all these values in one dimension part. So this operation is called flatten, right? So we are going to flatten this one. We are getting this one dimension output. We are applying the fully connected layers on this one dimension output, right? So this fully connected layer will do the classification, and then a final layer also like the fully connected one. And here we can take any number of neurons. Just if you are aware about artificial neural network, the same concept here. But in output class, in output layer, we should have like the number of neurons in the output layer should be equivalent to the number of classes here, right? For example, we are classifying 10 different types of vehicles, right? So we should have 10, 1, 2, 3, 4, like that. Okay, so we should have 10 different outputs in this output class. So that output, those outputs might be car, truck, van, bicycle, like that. Okay, so this is the way we apply all these operations. And one more important point, uh, we apply some activation function every time. Like for example, we are applying ReLU here, right? We are applying again ReLU here. But in output class, in output layer, we will apply activation function based on our requirement. Based on requirement means, for example, we are doing multi-class classification. Means there are so many classes, more than two classes in our data set. Then we should apply softmax activation function. So what softmax activation function do? It generates a probability corresponding to each class. So for example, there are 10 different types of vehicles. In input, we have a car, like actual input is car. So it generates the probability means, it generates the probability means like for car, it will generate the probability between 0 to 1. So in input, we have a car. So for car, it will generate the probability like 0.6. Why it will generate 0.6? Let's say because it will compare the features like our model, fully connected model will compare features of car. So for example, in car we have a round steering, we have four wheels, we have like different colors of car, right? And so many different features, other features we can compare about a small size of wheels, right? Two small headlights on the front, right? Rear sensor camera, front sensor camera, like that. Then we have truck. In place of car, we have a truck. Truck means like the different body than car, bigger steering, bigger vehicle, bigger wheels, right? In truck there might be six wheels in place of four, right? So based on the features, it will give the probability for truck. So but in input there's a car, so it will not, these features will not match with a truck, but a few features of truck are similar to car, like total number of wheels, it might be like four, might be six, and steering, round steering, headlights, right? Sometimes color, right? So for truck, it will give a probability just like a 0 point, let's say 0.1. Okay, few features are matching. In a similar way, for van also like 0 0.1, it will give you features, right? In the same way, like for example, there's a bicycle. The features of bicycle are completely different than a car or truck or any other vehicle, right? In bicycle, we have a handle, right? And in bicycle, we have only two wheels, and bicycle gearing style, braking style, everything is different than this car. So for bicycle, it should give very low probability, like 0.0001, let's say. Okay. So in this way, why I'm going to explain? Like here, you will find the probability corresponding to each of the category. So if for car, the highest probability, right? So that's why for car will give you the answer, right? So if your input is car and the highest probability is there, then our output will be corresponding to the highest probability. And here in this case, highest probability is for car. That's why like it will tell like in the picture there's a car, right? So this is a basic concept behind this deep learning approach and how they apply. So this part is called feature learning. This part is called classification, right? Now here we can like understand the same thing, filtering mechanism, which we already did earlier. So you already know at this moment like about the things. So for example, this is an image, this is a filter. We are applying image to filter. Then element by element we will multiply 0 multiply by 4 plus 0 multiply by 0 plus 0 multiply by 0 like that. So element by element we will multiply. Then we find the addition, and summation is -8. Then this center pixel will be replaced with a -8, right? So this is the way we can apply the filtering. Now let's explore this thing in bit more detail, right? Now we are going to explain about down. Now we are going to discuss about the convolution layer, which we have seen earlier in linear model, right? So how convolution layer work and how we can find the features from the convolution layer that we need to see. For example, we have like to understand this here. If you will focus on a screen, then you will never forget about a convolution layer after this class. So, like for example, we have image, one image of size 5 cross 5. Why it's a 5 cross 5? Because this is the actual image. It's a blue part, light blue part is the actual image, right? 5 cross 5. This 5 cross 5 is the actual image. Right? It's the actual image, 5 cross 5 by light blue part. Here we have 5 cross 5 image. I will explain about all these things, other part. And this is the RGB image in which there are three channels. I already explained about the RGB, right? Image part. So just I'm not going the deep of that part. We have RGB image, red, green, blue image. And each image size is 5 cross 5, right? Just neglect this part like this, 5 cross 5, right? Each image size is 5 cross 5. There's a red channel, green channel, and blue channel. And all images will be of same size. Now, we have this 5 cross 5, these values are there, pixel values are there. Now, if you will apply operation, if you apply convolution operation on this one, filtering, just like a filtering we did earlier, then what will happen? First of all, we need to select the filter size, what size of filter we should choose, right? So for example, we need to take 3 cross 3 filter. So we are going to take 3 cross 3 filter here, right? If we will take 3 cross 3 filter on this part, right, then what will happen? Our image is this part, right? If you're applying 3 cross 3 filter, then there is no value here. We will not get any value. We will not get any value here in this part, right? So what we need to do? We need to pair some information, right? So to make efficient operation for this corner pixel value, like this one, this one, this one. So every pixel value will face problem, right? This one, right? Because we don't have a complete, this 3 cross 3 filter will not completely cover all these things. So that's why we add padding. So this padding might be like 0, right? It might be 255. It might be a similar value like this one. For example, 0 is here, then 0, 0 is here, 0. If 1 is here, then 1, 0 is here, 0, 2 is here, then 2, like that. That is also possible. Because this is a single pixel location, right? Single edge, then it will not make a much impact, right? It will not take a much impact if you're going to go for in this way. So this is the way we do the thing. Then another important part, we have taken 3 cross 3 filters. That's fine. We have taken 3 cross 3 filter here. But as we have number of channels 3, 1, 2, 3. So that's a reason like we should go for 3 different channels here, right? One channel for R, another channel for G, another channel for B. Mean filter also we should have a 3. If there are 3 here, then we should take a 3. It's a mandatory condition. But this 3 cross 3, this size 3 cross 3, it depends on us, right? We can change this size. We can make it 5 cross 5, 7 cross 7, depends on application. If, for example, we are detecting large object in an image, then we should go for large object with a similar color. Then we should go for large filter size. If we are going for a smaller object, then 3 cross 3 is okay, right? So accordingly, we can do this. And we have bias, right? Bias is to adjust the value. So now at this moment, just forget about this thing, right? So we are going, we got our 3 cross 3 filter, and this 3 cross 3 cross 3 size is there, W0, 3 cross 3 cross 3, like that, okay? Now, what we need to do, just remove all the ink. We need to apply the filter, right? If you see this animation, then this animation is applying convolution operation. So let's just forget about the animation, focus where I'm going to point. So for example, we are going to apply 3 cross 3 filter on this part, right? Means we are going to apply on this pixel position, the center pixel position. We'll take 3 cross 3 neighbors like this. Then what we'll do, we'll take the element by element multiplication. So like 0 multiplied by -1, so it's a 0, then plus 0 multiplied by 0, 0 multiplied by 0, right? So again 0, right? 0 multiplied by 1, then again 0. Likewise, all will be 0 because these are all 0 values except this one. So this 1 multiplied by -1, so it will be -1. So if you find the summation of everyone, then we'll get -1. So we are getting -1 from here. Next, now same way we need to perform operation on this part, right? On this part. So here what we need to do? 0 multiplied by -1, 0, 0, 0, everyone 0. Just take this part. 2 multiplied by -1, so -2. 1 multiplied by 1 plus 1. 2 multiplied by 1 plus 2. And 1 multiplied by 0, 0. So everything will cancel out, just 1 will left. So like that, 1 here. Okay, same way we do for this one. So 0, 0, 0, everything 0. 2 multiplied by 1, so 2. 1 multiplied by 0, 0. 1 multiplied by -1, so -1. So again, we'll get 1. So 1 here, right? So we got all these 4 values, 1, 2, 3, 4. Then we will find the summation of all these 4 values. Then 1 minus 1 cancel out, 1 plus 1, 2. So we'll get 2 here, right? So we are getting 2 here. In this way, in a similar way, what we'll do, we'll calculate for next. Here, for calculating next, we need to discuss about these parameters. Here we are taking stride s equal to 2. by default stride is equal to 1. But we can change the stride value depends on the image size. For example, our image is very high, image of very high resolution, and there are large size objects are there in the image. Then we can take a higher number of stride. So if you're taking this higher stride, then that means like we are reducing the complexity. We can reduce the complexity of model. Complexity in the sense like you have seen like so many multiplication and addition we are doing. So we can reduce those multiplication and addition if we are taking higher value of stride. So if you're taking stride value 2, let's say first understand stride value 1. So like if we have, for example, we applied on this one. If you are using stride value 1 means we will drag this window one position. We'll drag this window one position, right? Next we will drag this window one position like this. Okay. In case if you are using a stride value 2, then what we'll do? This is the first image. If you're taking stride value 2, that means take another color, then it will be better. Then for a second image, from this pixel to this one, we will move. So that means we are leaving one here like this. Okay. So here like we are leaving one pixel value. Now this one to this one will take. So here we are leaving one pixel value like that. Okay. So in this way, so many multiplications we are going to reduce, so many complexity we are going to be reduced. So a similar way, like we'll calculate for a stride value 2 and we'll find all these things and we'll get this value. Then again for next one, this value, like this one, like that. Okay. We'll get all these values with the help of stride 2 and that's it. Now we covered this part. Now you might be worrying about the another things. Why we are using another filter. In image, there might be different kinds of features, right? For example, let's say very simple example, like for example, like we have a horizontal, we want to detect horizontal images, horizontal edges, and vertical edges. So let's say this first filter might be used to detect horizontal edge, and second filter might be used to detect the vertical edges, right? So in this way, like we can detect the horizontal edge from this one, vertical edge from this one, and mechanism is same for both. So we'll get this output from first filter in which we have a horizontal edges, and this output from second filter in which we have vertical edges, right? Horizontal and vertical edges we have, right? And so we have written number of filters to W0, W1, but in reality, these filters might be more than 2, maybe 10, maybe 20, maybe 100, right? So depend on your image. And number of channels are 3. So 1, 2, 3, and padding is 1. So padding bit is 1, like we added padding bit all around the image, right? So this is the way like we do this convolution operation. I hope you understood. If any question, let me know. So we did all these things. We understood about input image. We understood about filters. We understood about stride, filter, stride, channel, padding, right? So convolution layer consists all these things. Now there might be a question in your mind. For example, we are giving the input image size. We are giving some filter size. Can we detect the output size directly without doing all these things? Right? Then yes, we can do that thing. For example, our input size is n cross n. Our filter size is f cross f. Then our output size will be n minus f plus 1 cross n minus f plus 1. This is applicable only when we have stride equal to 1, means by default stride, and padding equal to 0, means we are not adding any padding bit. Right, this is applicable. But what will be the output? If we have different values of stride and padding, then we have something different. For example, we have a padding bit, not the stride one. Stride is only one. So then this is the case. N plus 2p minus f plus 1, n plus 2p minus f plus 1. If we have a stride also, then f plus 2p minus f divided by s plus 1 divided by s plus 1. If a stride is equal to 1, then it will be similar to this one, right? If a stride is more than 1, then this formula will be applicable. Okay, so now as I promised you, I need to go back to that particular figure, this one, and I need to explain you how it can work. Like for example, our input size is 32 cross 32. And after applying convolution layer, how we are getting this thing, right? So let me explain one more thing, then it will be complete. So it will be completed. So here, like for example, like we have n cross n size of image, nc is the number of channel. Then obviously our filter size will be f cross nc, right? Nc. Then our output size will be n minus f plus 1, n minus f plus 1 cross nc dash. Our output size will be nc dash here, right? So this NC is different, NC dash is different. NC is the number of channel, NC dash is the number of filters. Very important point, right? So let's understand with the help of this example. In this example, we have number of channels 3, 1, 2, 3, but number of filters are 2, 1 and 2. So our output size will depend on number of filters. How many outputs? 1 and 2. So first output for first filter, second output for second filter. This is called NC dash. NC is this number of channels. So number of channels will not be decide the number of output, right? So make sure about this thing. Okay. So we understood all these things. Now move back to this figure. In this figure, we have n equal to 32, right? Our f filter size in this case is 5. In linear model, filter size is 5 cross 5. So we are taking f equal to 5. Then after convolution layer, our output should be n minus f plus 1. I told you, right? Formula. If we have a stride 1, padding equal to 0. So n minus f plus 1. So n is 32. F is 5. 32 minus 5, 27 plus 1, 28. So that's the reason we'll get this 28 cross 28 image. And in this case, we are using 6 filters, right? So that's why 6 cross 28 cross 28. I don't want to write cross here because this is a filter. These are the image size. So 6 cross 28, you can like understand. So you can see 6 filters, 1, 2, 3, 4, 5, and 6. You can see 6 filters are there, right? 6 outputs, just like this. Here we are getting 2 outputs, right? Last green color. In the same way, we'll get 6 outputs using this one. Now, similar to this one, use a pooling layer. We'll understand pooling later on. Now, for example, we have 28 cross 28. So, for example, like we got after pooling, we got this 14 cross 14 and 6 1. We are again applying convolution layer. Then n minus f plus 1. So n is 14 minus f is 5. 14 minus 5, 9 plus 1, 10. So that's why we are getting 10 cross 10. And in this case, we are using 16 filters, right? So if we count, these are 16, right? 16 filters. So output is 16 cross 10 cross 10, right? So this is the way we can apply this convolution operation, convolution layer. And here also we can see directly, we can see operation. Like for example, our input size is 5, n equal to 5, padding equal to 1, stride equal to 2. Then our formula just f filter size is 3, right? F is 3. Don't be confused. Number of filters are 2, but filter size is 3, right? I'm talking about the size. Filter size is 3. So the formula will be n plus 2p minus f, right? Divided by s plus 1. If we calculate this one, n equal to 5 plus p equal to 1, f is 3, divided by s is 2. If you write all these things, then answer will be 3. Just you can try. So it's a 3 cross 3 will get output as a 3 cross 3 side. Right? So this is the way we can work for this convolution layer. I hope you don't have any question in this convolution layer part. Now, one more other important thing in convolution layer is number of parameters, right? We measure the complexity of model with the help of number of parameters. So how to find number of parameters? So in these filters, we have a number of parameters like filter W0. We have 9 values. 9 values. Here also we have 9 values. Here also we have 9 values, right? So these are the parameters. So we have 12, total 9 plus 9 plus 9 plus 1. Total 28 values we have, right? 27 plus 1, 28 values we have, right? Like we are likewise, same 28 values we have. So these 28 values are nothing, just a parameters. 28 plus 28, total 56 parameters are there in this model, right? So we can say in this small model, there are 56 parameters, but in reality, these parameters are in million, right? So similarly, like if we are going to calculate the parameters for the 10 filters, right, with 3 cross 3 size image, one bias, so there will be 281 because in one these are 28, right? We have seen earlier, and then in 10 it will be 28 multiplied with 10, so 280 number parameters. Okay. Right, so this is the beauty of deep learning algorithm. If we are going to use like ANN in place of this convolutional neural network, then in ANN there will be higher number of parameters for this many filters and this many layers, right? So we are not going deep of that thing. And if there are high number of parameters, that's why it becomes the problem of overfitting in that convolutional neural network part, in that ANN part. So after a convolution layer, we apply different activation function. The task of activation function is to activate a particular neuron. So there are different types of activation functions are there like sigmoid, tan hyperbolic, ReLU, leaky ReLU, max out, and ELU. So based on different purposes, like we use those activation functions. And like ReLU activation function is for like nonlinear case, mostly for nonlinear case, right? It looks like linear, but it's a nonlinear because below low up like below zero there is no value, right? So like that. Okay, so this is the way like we can do all these things, leaky ReLU and other max out, we can do all these things for it, right? So we just activation function used to activate a particular neuron. Next layer is max pooling. So here what we are doing, max pooling, the main task of max pooling is to reduce the complexity, right? For example, we have this 4 cross 4 image, right? In this 4 cross 4 image, we are applying the max pooling, 4 cross 4 max pooling. Then, yes, we are talking for max pooling. Then we'll take the maximum value out of this. And the maximum value is 9, so we'll take 9. Next, if we have 2 cross 2 max pooling, non-overlapping max pooling, 2 cross 2, then we'll go for this 2 cross 2, right? So we'll take 2 cross 2 window, right? And it's non-overlapping. Then again, we'll take next 2 cross 2. And out of these window, we'll take maximum values of 5 here, 6 here. Like that, we can take all these values, 2 cross 2 next pooling. Then if you're talking about max overlapping part, then we have this one, then so overlap from here, like that. We can do all these things, 5, 5, 6, 8, 8, 9. We can do all these things, right? So n plus 2p minus f divided by s plus 1, we can do all the help of this max pooling. Right, so it's very simple operation. Just we need to divide according to window size and make the half. Take maximum value. So let's, if we are moving from here, here we are applying max pooling or pooling, we are applying pooling operation or max pooling, whatever. So here like we need to apply the pooling operation on this 28 cross 28 cross 6. Then what it will do, and we are taking 2 cross 2 window size, then it will make your size half, 28 to 14 it will make, right? But it will not change number of filters. Number of filters will be same, 6 cross 14 cross 14, right? And the same way likewise here also 16 cross 5 cross 5 will make a, we can make this with, okay? So this is the way we can do all these things with the help of max pooling, right? Just making the size half. Very simple. Okay, next is a fully connected layer. In a fully connected layer, just like artificial neural network, neurons are connected and they are passing information, and just we are getting the output, right? So I'm not going deep of this one due to time constraint, but here we can understand this fully connected part. Like for example, we have got this one, and from this one to this one we are getting, and like this is fully connected, so this will be a connection all over there be a connection, right? All over there be a connection like that. Okay, it's a fully connected layer, so everywhere there will be a connection like this. Okay, and there's a number of outputs 10, so we are going to predict the 10 different outputs. So that's why this value will be 10 here, right? So this is a fully connected layer part which is used for classification purpose. Now this is done. And softmax activation function concept, I already told you, it generates a probability in the last layer. Now there are different CNN architectures. Like we discussed only one CNN architecture, LeanIt. But along with LeanIt, there are other architectures like LXNet, VGGNet, GoogleNet, RegNet, ZFNet. These architectures are useful for various purposes, right? So here they we can use this architecture for like mainly we use these architecture are pre-trained. If you're talking for VGNet, GoogleNet, RegNet, ZFNet, they are pre-trained on large datasets like ImageNet dataset. In ImageNet dataset, we have like millions of images and 1,000 classes. And on that particular dataset, like the VGNet, RegNet are trained. This trained here means like if we are going to like for example, come back to that diagram here. Here, if you are working on this small architecture in which there are only two filters, right? We are applying convolution layer. In these two filters, in the beginning, we randomly assign these values. Any value we can assign, right? Any value we can assign. But as we are going from like input to output, and we are moving back from output to input, means forward propagation, back propagation we are doing. The task of forward and back propagation is to learn all these features, learn all these features effectively, learn all these features effectively, right? Learn all these parameters effectively. Try to find appropriate parameters. So in each of the iteration of forward and forward propagation, back propagation, we adjust all these values. We adjust all these values. We adjust all these values, parameters values, right? So in the end, we are expecting like these parameters value are final. These parameters values are most appropriate, very good like parameters value means we can generate the output for unknown input also with the help of these parameters value. So the task of training means we need to find these parameters value, right? We find the features. Now, as I'm discussing here about this LeanNet, LXNet, and pre-trained model. So pre-trained model means, like for example, we are talking about BGNet. Here, pre-trained model means we have already trained our model, right? And that trained model we can use for our different purposes. So, for example, we are talking for VGNet architecture. In the VGNet architecture, there are 16 layers, 19 layers, depends on the type, what kinds of architecture you are using. Those 16 and 19 layers are already trained on ImageNet dataset. Already trained means they have already calculated the weights. They have already calculated the weights, right? These weights from the parameters. Now we can directly use these weights for our application purpose. For example, they are trained on ImageNet dataset, which is a very large dataset in which there are 1,000 images. Now we collected some data set from our local community, like for example, pet classification, right? Dog classification, different breeds of dog we need to classify. And we have only 200 images, right? So if you are going to apply 200, apply deep learning model with the help of using 200 images, definitely 100% you will not get very good accuracy, right? So what is the option? You can use the weights of this VGNet by downloading from internet, and in those weights, just change the last output layer, right? Because in the last output layer, what is there? If you see, go through this figure, in last output layer, what is there? Like classes, right? So if you're talking for BGNet, ImageNet dataset, then in those cases, we have a 1,000 classes. But here we don't have 1,000. In our case, just for dogs breed classification, let's say like 5 different types of breeds are there, right? So then what we'll do, just remove this output layer. In place of this final output layer, just put your output layer with 5 classes, right? Put out your output layer with 5 classes and keep all the weights as it is, all the weights as it is, and train the model slowly for 5 to 10 epochs, 5 to 10 epochs means 5 to 10 iteration, slowly with very low learning rate. And in this way, you can find better accuracy than like you are applying your model, your trained model on those 200 images, right? I'm not telling here you will get very high accuracy, but you will get better than applying the model from scratch. So this is called like a deep transfer learning. Pre-trained, we are going to use a pre-trained model for transfer learning. So these all models can be used for the pre-trained. You can find the weights of all these models from internet directly from TensorFlow or PyTorch, like whatever you prefer, right? So you can find those pre-trained model and you can apply this thing, right? So it's very famous and people use a lot. And another advantage of this pre-trained model is to like complexity. If you are training the model from scratch, then you need very high GPU, right? GPU processing power. But like if you are going to use pre-trained model, then you don't need that much GPU, right? So this is the advantage. Now, let me see the time. Then accordingly, I will cover other parts. So there are 10 minutes. So let's see. Okay, so we have another variant of this CNN model. There are so many variants. One variant is unit. Although CNN convolution neural network is highly popular, right? But if you're talking for high accuracy, especially in the domain of medical imaging, we need very high accuracy, right? So if you're talking for very high accuracy, then we should go for this unit model. In this unit model, we have like so many convolution layer, and we have like encoder, like we have this encoder side, right? And we have decoder side, other things like that. So if it if we start from the beginning, like we have input image of size 572 cross 572 cross 1, right? And as this is the one, so it's a grayscale image. Only one frame is there, right? So it's a grayscale image. And on that image, we are applying convolution operation, right? This blue represent a convolution. You can refer from here. Convolution 3 cross 3 value. If you are applying convolution operation of filter size 3 cross 3, you are intelligent enough now. Like for example, input size is 572 cross 572, n equal to 572, n is 572, and f is 3, right? So you can get like n minus f plus 1. So 572 minus 3 plus 1. So 570, right? So you will get 570 cross 570. In the same way, you will get 568 cross 568 after another convolution layer. And here we are using 64 filters. That's why it's a 64 and 64. Likewise, we can use max pooling. So max pooling will make the size half. So 568 divided by 2. So 284. And this number of filters will be same, 64. You already know, like max pooling does not change the filters. So 64 will be same. Then again, we are applying convolution. Then 284 will become 282 using n minus f plus 1, like that. So same process will be repeated. And in last, just we'll get this 28 cross 28 or 30 cross 30 size. And here, these are the just important features. These are representation of the complete image. These are the representations here. So then this is a very small image size, right? 28 cross 28. Then it might possible, and in most of the cases, we lost some important features, right? We lost some important features. So what we need to do? We need to go back, move back to upsampling. So 28 cross 28 will become like 56 cross 56, the opposite of the convolution operation. Like again, convolution we are applying, then 52 will become 104, like that. So we want to reach at the original image size. Now, in all these process, we can think over like we might have lost some features, right? Because here like 28 cross 28 we got from 570 cross 572 is a very small, it's a huge difference between both. So we might have lost some features. So to preserve those features, we use a skip connection. So there are skip connections between input image to output image, between input image to output, between input image to output image. Right, there are skip connections between input image to output image we have, right? So this is the way like we do, and like we apply all these operations, and we get the output. And here the classes are only two, like in this case particular data sets, because we are going to like segment a tumor, let's say, right? A medical image tumor. So two classes, so foreground and background tumor, we can do all these things, right? So this is the way like we apply this unit model, and we can work for this thing. Okay. This unit model is highly popular in medical imaging domain. So we can see all these things like how we can apply this unit on medical domain. So let me see what else I can cover. Okay, that's fine. So here, like we are talking for training, validation, and testing. So now let's explore some basic operation of this deep learning. We apply like training, validation, and we divide our data set into train data set, validation data set, and test data set. So here we will learn why we will divide into these three parts and what is the role of this each of the valid data set. So if you're talking about training data set, the sample of data used to fit the model. Training data set is used to sample data to fit the model. Validation data set is used to validate a model. So for example, we are applying the data set for the small kid, right? We want to classify a kid into particular part, right? Not kid, a particular part. For example, there is a small kid, and in the beginning, the age of kid is just like a 2 or 3 months or 4 months, 5, 6 months. Then at that time, that kid does not know anything, right? So what we can do, that the kid can touch the fire, that kid can fall from the height, right? Bed and other place. So if the kid is going to touch the fire and the kid is going to touch is falling from the height, then their parents, their elder brother and sister tells him or her like don't touch the fire otherwise it hurt you. Don't go beyond this point from the bed otherwise it will hurt you, right? So again like kid repeat the same mistake, right? Again and again they do the same thing. They do like a kid do the same thing, right? So in this way like a kid get mistake, kid do mistake, but after some time kid understand other things. Oh, I should not touch the fire, I should not go beyond this point from the bed otherwise I fall down, right? So means kid is taking training, right? Kid is getting trained slowly. If for example the age of kid is 4 years, 5 years, then in that case the kid will not touch the fire, kid will not fall from the bed, right? So that part is called training data set. And our training should be strong, right? Our training should be strong. That's the reason we take large chunk of data for training purpose, right? To make our strong model, strong training environment. Next is validation data set. Validation data set means during training time, like parents are giving training to their kids, like don't touch the fire or don't fall from the bed. Then they want to test their kid, right? Whether like kid is learning properly or not. For example, they trained a kid for one particular kind of bed and they want to test on other type of bed, right? So they put a kid on another type of bed and will ask kid, okay, jump from the bed. If kid is not jumping, that means training is going in the right direction. If kid is jumping, that means training is not going in the right direction. That's called validation. They are validating the information with the help of the other kinds of data set. Next is test data set. After like for the kid, the age of kid is 5 years and 6 years old, and the parent think like my kid is okay now, like 96 97% accuracy is there, 98 99% accuracy is there. Then they want to test their kid in different environment. So they will do, they will leave their kid in neighbor's house and relative house, right? Neighbor's house, relative house is completely different, right? And they will ask, and neighbors at this time, neighbors will ask, their kid to jump from the bed or jump from particular height or touch the particular fire, like that. Okay, so in that case, if kid is not touching the fire, kid is not jumping from the bed, that means our test accuracy is very good, right? So here, that's a region. This is like one of the kind of case study I related with the machine learning. Machine learning model also work in a similar way, whatever I explained. So we divide our data set in training, validation, testing, right? And accordingly, we can do all these things, right? And we should use validation and test from the same type, similar types of distribution, like Gaussian distribution or some other types of distribution, whatever, but it should be similar kinds of distribution. Then we'll get the higher accuracy. And in training, we have so many different types of hyperparameters like learning rate, iteration, number of hidden layer, hidden unit, like choice of activation function, like that. We could do all these things, right? So this is the way we work on this training, validation, testing part. And once like we are training our model, like we are applying training, validation, testing, and other things, then in a training part, it might possible like we can get some problem like underfitting problem, overfitting problem. So underfitting me problem is like sometimes just let's take the similar kid example. Sometimes the parents are very lenient, right? So they don't care about their kid and whatever they are doing. So lenient mean like just their single line, and there are so many error in the training part as well as in the testing part, right? The opposite of underfitting is overfitting, means the parents are very strict towards the rules, right? So they want like 100% accuracy in training case, right? But if there is 100% accuracy in the training case, then what will happen? The model means that kid will learn, that kid will mug up everything, right? So if they will mug up everything, in this case, like they will go in other environment, testing environment, then they will fail. So training accuracy is very high in this overfitting case, but testing validation accuracy is very low. So what we should do, we should go for appropriate fitting. Means we should allow some little bit error in a training case. Similar kinds of error will be in the testing case also. So this is called like high barriers, high bias thing, and we can do all these things with the help of. Okay, so this is the way like we can do, and I'm getting message from like madam, like we need to conclude the talk. Okay, so let me quickly give you some application part of this computer vision application part of deep learning. You can use this deep learning in object detection, object tracking, recognition, face recognition, action activity recognition, right? Human pose estimation, image classification, and so many other application areas. So if you want, you can take the screenshot of this image, a screenshot of this screen, this like slide, and these are highly important application areas nowadays, so you can work on in all these parts at this moment, right? So this is the way like you can go ahead, and that's all, and thank you very much. Please let me know for any question. Thank you. All done, madam.
Thank you, Sanjeev sir. Actually, Sandeep sir, sorry for telling
No
you that
problem,
to
ma'am.
conclude.
No
Okay.
problem.
So that was really a wonderful session. Really, it was really helpful in understanding the deep learning and its applications. Thank you so much for joining, sir.
Yeah, thank you, madam. I'm leaving now, right?
Yes, sir. Thank you so much, sir. Thank you
Yeah,
for
madam.
joining.
Bye. Bye. Bye.